So welcome to the 5th class of this course. So briefly I will introduce that last class we discussed about the field reduction factor, image compression factor and the importance of cryogenic temperature on the field ionization. So I will just briefly touch on those terms so that we can we can move forward. So as you see in the slide, we have defined the field reduction factor Kf, okay, and which directly depends upon the shape of the tip, especially the shank angle. Shank angle is nothing but a half angle at the apex of the atom probe or the needle specimen, correct. And this field reduction factor is takes care about the so as the shank angle is less lower, that electric field the distribution of electric field is more dense at the needle specimen. So your Kf will become near to will be reduced, fine. And the importance of cryogenic temperature, the cryogenic temperature is important to lower the thermal agitation of the surface atoms, okay. What will happen if this is done, then what you can do is the thermal accommodation of imaging gas is more efficient, okay. So and this is due to the reduce in the thermal energy which is directly related to KBT of that particular imaging gas, fine. And this cryogenic temperatures also decreases the lateral velocity, which I will briefly discuss about lateral velocity on the importance of the resolution, or because thus it improves the spatial resolution, okay. So this we have discussed in the last class. Then we also discussed about the image magnification. So this is last class I have drawn the schematic. Now you can see here, this is your needle specimen, this is your phosphorus screen, okay. So due to the image compression factor, the field lines ideally the field lines should be radial in this direction, but due to the image compression factor, so what will happen, these field lines will try to bend in this direction, fine. So it will be compressed towards the main axis, the central axis of the needle specimen or the phosphorus screen, okay. So now if you see these triangles, if you see these triangles, okay. So now this is your this particular triangle, and this is the distance which we call as a D, okay, and the length from the tip L, fine. So now the distance between the surface atom and the axis can be regarded as D, fine. So and now as these field lines are not at the exactly at the radial direction, these are bent towards the axis. If you project it, it will go to a position away from the center of the needle specimen or the center of the tip radius, fine. So that can be given by a xi r, okay. Xi is the image compression factor, okay. So now if you see as you can see that this particular xi r is much lower than L, okay. So if you see these two triangles, triangle 1 and triangle 2, okay, and if you apply analogy, then you can deal with the M projection as D by D, means the distance between these two, D by D is may be equivalent to, as xi r is less than L, we can write it as a L by xi r, fine. So this is the assumption that, so usually ideally it should be L plus xi r divided by xi r, but as you know that xi r is much less than L, so we can neglect this term. So magnification is given by L by xi r, fine. And xi is the image compression factor. And we also talked about the crystallography. So as I told that in the film image you have these concentric rings, and these rings corresponds to a particular crystallographic direction. So this is a tungsten BCC, tungsten BCC. This is a FIM image of a tungsten BCC needle specimen, and you can see that these concentric rings are exactly at certain crystallographic direction. These are nothing but stereographic projection. Okay, so what we can do is you can actually, and these rings you can know, we know that in a crystallographic direction the angle between the two directions remains same, and it can be calculated. Okay, it remains same, it can be calculated. So what we can do is we can measure the observed angle theta observed between the two zone axis or the two crystallographic axis, and we can also calculate by simple equation of cos theta, which depends upon h1 k1 l1 and h2 k2 l2, that theta crystallography. And xi can be calculated or estimated by theta crystallography by theta observed. Okay, so by finishing some more classes, we will have some small mathematical questions where we can calculate the image compression factor for different types of FIM images. Fine. Next is just briefly projection of ions. So image formation, how image is formed. As I told you, you are applying a positive voltage on the needle specimen, and you are passing an imaging gas. Okay, and this imaging gas actually it get polarized near to the tip surface, and due to polarization this gas converts to plus ions. Okay, positive ions, and these positive ions will be accelerated towards the phosphor screen by the electric field. Okay, so this is the brief introduction, brief review of whatever we discussed in previous classes. So now we also little bit discussed about the resolution of a microscope. So how it can be compared to the FIM. Okay, usually the resolution of a microscope we can define as the two images are just resolvable when the center of the diffraction pattern, or when the center of an intensity, the maximum intensity is overlap with the minimum intensity of the another image. Fine. So that is the Rayleigh's criteria of the resolution. If these two points are overlapped, then you cannot distinguish, you cannot resolve that two object features. So this is the definition, a typical definition of a resolution in a microscope. But what is the definition of FIM? FIM, the definition of FIM relies on the size of the smallest image spot on the screen. Okay, and there are three major factors which governs or which controls the image spot on the screen. These three factors are size of the ionization zone, which is formed just above the tip surface, the lateral velocity of the imaging gas, and also the position uncertainty of the imaging gas. Okay, so I just briefly gone through it. So now we will discuss these three factors which influences the image spot in little bit of elaborate way. Okay, so first we will discuss about the size of the ionization zone. Fine. Size of the ionization zone. What is the size of the ionization? It is the, so this size is of the same order. First factor, same order as the size of the imaging gas atom. Imaging gas atom. Okay, and it critically depends upon the amplitude and distribution of electric field above the atom on the tip. Okay, so what are the two important factors which are critical? One is amplitude and distribution of electric field. So if the field is very relatively low, so as we discussed in the third class, if the field is relatively low, the critical distance xc where this is the optimum distance where you can get the tunneling effect. So the critical distance xc will be very large. So if xc is very large and because of low electric field, then the whatever the imaging gas is there, whatever, so this is the atom probe tip, these are the atoms on the tip surface. So the imaging gas which is on the surface near to the tip surface, if the xc is very large, then what will happen, it will not replicate exactly the position of the atoms. Okay, it means that it will not reflect the structure of the surface of the atom on the phosphor screen. So means it cannot mimic the structure of the atoms which are on the surface of the tip. Fine. So xc should not be as large, so low electric field you cannot image the exact structure of the tip. If xc is very small, means not so if the electric field is very high, then what will happen, the gas atoms are very close, the gas atoms are very close to the atom probe needle. Okay, what will happen if the gas atoms are very close to the atom probe needle, if you magnify this part, if there are two atoms, so the ionization zone which is created by the gas atom, it will be overlapped between the two atoms, then you will get the blurred image. You will get the blurred image. So there is a term which we need to define, is the best image field, which is called BIF. So this is a very important term by which this is the field. What is the definition of this field? This is the field for which the volume of ionization zone is minimal and which produces highest resolution. Okay. So this BIF is directly depends upon the imaging gas, especially the evaporation field of the imaging gas, or what we can tell the ionization energy of the imaging gas, ionization energy of the imaging gas. Okay. So different gases can be used for the imaging, correct. So different gases have a different BIF value. For example, for helium, which has a ionization of 24.6 electron volt, it has a BIF value of 44 volt per nanometer. Okay. Similarly for argon, the ionization is around 15.8 electron volt. So there the BIF value is 22 volt per nanometer. Okay. So depending upon the imaging gas, you have a best image field where you are getting the volume of the ionization zone is minimum and also with a highest resolution. So it is a balance between the low electric field and high electric field. Okay. So this is the size, this is the importance of the size of ionization zone. Now coming to the lateral velocity, the second term. This is the first term, the second term. So ions are formed when the gas atoms jumping through the ionization zone near to the surface. Okay. So you have a atom probe needle, you have a ionization zone on the atom probe tip. So these gas atoms are jumping across this ionization zone due to the electric field. Fine. And their velocity, jumping means they have a certain velocity, and their velocity has a component parallel to the tip surface. That totally depends upon the kinetic energy, and this kinetic energy depends upon the tip temperature. Okay. So this is how it is related to your cryogenic temperature, that is why we keep. So the kinetic energy depends upon the tip temperature, kinetic energy of the imaging gas, and this kinetic energy is directly contributes to the lateral velocity which is along the tip surface. Okay. So after the field ionization, the gas ions is projected from the vicinity of the tip onto the screen. Hence, if the ions have a components which are generated above the single atom have a statistical distribution of velocity, initial velocity in lateral or tangential, then it will not follow the same trajectory. It will have it is a disturbance at the when it's striking to the phosphor screen. So since these trajectory aberrations induce, so this will induce a spread. This will induce a spread on the ion impact on the phosphor screen. So that's why we don't see a point, we see a spot, which is literally a spread which is contributed by the size of the ionization zone and also the lateral velocity. Okay, so this is the importance of the lateral velocity, which directly depends upon the kinetic energy, and this kinetic energy is directly related to your tip temperature. The third point is position uncertainty. What is position uncertainty? I think everybody must have heard about Heisenberg principle. Okay, so if any gas atom, it is very the position and energy of the atom cannot be precisely determined. Any gas atom, the position and energy cannot be determined at the same time. Okay, so for example, the de Broglie wavelength of helium atom, at a thermal agitation of 20 Kelvin is around 0.2 nanometers. Okay, so bigger than the size of the zone in which the atoms are ionized. Okay, so this is the position uncertainty. So you cannot neglect the quantum nature of imaging gas atom. Fine. So quantum nature of imaging gas atom. So this effect will be much less in film than in the in the second class I just introduced about the FEEM. Okay, so what is FEM? So I must revive you that this is the first microscope which was built by Mueller, where he used electrons for imaging. He has imaged the electrons. Now you can see that in the field ion, in FIM, we are using ions for the imaging to see the image on the phosphor screen. So ion is much heavier, electrons are much lighter. So what will happen? The position uncertainty of electron is much higher, but the position uncertainty of heavier ion is much less. So the fluctuation or the spread due to the position uncertainty of electron will be very high, but for ion it will be much less. So you can able to resolve atoms by using imaging gas ions. However, you cannot resolve less than 2 nanometers by using the electrons. So that's why Mueller we came from FEM to FIM to image the gas atoms. Fine. So now you can correlate how important is the position uncertainty for imaging on the phosphor screen. Okay, so here there is a simple equation to give a approximate spot size when an ion strikes to the phosphor screen. Delta 0 square is related to your size of the ionization zone. The second term is related to your lateral velocity. The third term is related to your position uncertainty. Now here the xi is the image compression factor. Fine. Your Kb is the Boltzmann constant, Kf is the field factor, okay, F is the field. Fine. Then here actually H is the Planck's constant. fine. H is the Planck's constant, and m is the mass of the imaging gas atom. Okay, so this is the resultant spot is the addition of square addition of and square root addition of size of the ionization zone, lateral velocity contribution, and also the position uncertainty contribution. Okay, I hope now you understand how the definition of resolution in film, which is directly related to the size of the smallest image spot on the screen. Okay, and also more important is why Mueller has gone through from FEM, field emission electron microscope, to field ionization microscope. This is directly related to the resolution, which it directly depends upon the position uncertainty due to the Heisenberg principle. Okay, and as I told you, these electrons are much lighter and ions are much heavier. The position uncertainty will be much higher for the electrons than the ions. So your resolution will be very less in FEM, but in FIM we can actually resolve the atoms. So now we will briefly go through the instrumentation, okay, which is very important to understand how the typical FIM is reconstructed at an early stage. Fine. So the instrument, usually the low temperature field ion microscope FIM is better described as low temperature sharp emitter field ion microscope. Okay, and this was first made to work, as I told you before, 1955 by Bahadur and Mueller, due to the when Bahadur has suggested to make the sharp needle and also to reduce the temperature at cryo temperatures. Fine. This I want. Okay, so this is a typical diagram, a schematic, where you can see that a chamber, the instrument has an ultra high vacuum chamber. Okay, so this is an ultra high vacuum chamber with the ultra high vacuum chamber with a base pressure of 10 raised to power minus 8 pascals. Okay, and this ultra high vacuum is achieved by a series or by the high compression ratio turbomolecular pumps. These are backed up by several rotary pumps. Okay, so rotary pumps will give a initial vacuum up to 10 raised to power minus 3 to minus 4. Then these are picked up by the turbomolecular pumps up to 10 to the power minus 8. So as I told you, for high resolution, the most important part is the specimen temperature should be at cryogenic condition. Okay, so in previous FIMs, this was the specimens were cooled down by using liquid nitrogen or hydrogen or helium. But now in the latest FIMs, they use cryostats. What are cryostats? They use closed cycle helium gas. Okay, and these can reach a temperature up to 20 Kelvin. Okay, so the specimen temperature can brought up to 20 Kelvin. The third important part is the very high DC voltage, which is applied on the specimen. So this is a specimen holder, this is your specimen tip. Okay, so high DC power supply is connected to the specimen in order to generate a very high electric field in front of the tip, high electric field. Okay, so first is high vacuum chamber, ultra high vacuum chamber, then after that tip to be cooled down to liquid nitrogen temperature by using cryostats, and application of a very high DC voltage to the needle specimen. Once this tip is stabilized and thermally stabilized, once the tip is positioned and thermally stabilized, so an imaging gas is introduced into the chamber with a very low, with a low pressure between 10 raised to power minus 3 to 10 raised to power minus 5, 10 raised to power minus 3 to 10 raised minus 4 pascals. Okay. So, here the imaging gas, the most commonly used imaging gas are helium, neon, sometimes also hydrogen is used for in some cases. And also we can use the multiple combination of gases, because as I told you, these different gases have different field, different ionization energies. Based on that, they have a different BIF values. So, depending upon your sample, depending upon your sample crystal structure or sample phases present, you can use the mixture of gases to resolve that particular atomic structure of the needle specimen. Correct. So, these are the 4 important things. Now, coming to the after imaging gas, the one more important part is the phosphor screen. So, in previous FIMs, in old FIMs, the detector is just a single phosphor screen. Okay, and these ions, as I told you, are very heavy. The imaging gas ions which are polarized, when they strike to this phosphor screen, usually this phosphor screen gets damaged very easily. Okay. So, and the field, and also the problem is, as I told you, these field ion images are extremely dim, because I'll come to that. These field imaging gases, they will release very few photons per ion. Okay. So, previously they were used only the phosphor screens. Now, now in the new FIMs, just in front of the phosphor screen, they use another plate which is called a MCP plate. These are called micro channel plates, MCP plates. Okay. So, these MCP plates, the most important function is they amplify the signal. Okay. How it gets amplified? So, this increases the gain by 1000 times. By converting, how it comes? They convert the ions to electrons. Fine. They convert ions to electrons. So, and these electrons which are generated by these MCP plates, I'll come to, I'll describe the function for this. Once the ions, the heavy imaging gas ions hit to the MCP plates or microchannel plates, what will happen is these ions gets converted to very high number of distribution of electrons, and each electron will produce at least 100 times more than the photon, 100 times more photons than the ion. So, that is why you will get a very bright intensity spots on the phosphor screen. Okay. So, this is the role of MCP plate. Remember, the gain increases by 1000 times as compared to the ion striking to the phosphor screen. Okay. So, MCPs, as I told you, these MCPs are located just 1 to 2 mm distance apart in front of the phosphor screen. So, this is a MCP plate, this is your phosphor screen. Fine. So, the distance between these two is 1 to 2 mm. These MCP plates are nothing but a microchannel plates. Okay, and these are acts as a image intensifiers. Now, if you talk about multi-channel plates, here in the right side, in the left side, I am showing you a mesh type of thing. This is a typical MCP plate which is seen in the exactly in the perpendicular direction. Okay. So, it is nothing but a thin disc containing 2-dimensional close packed array of glass tubes. These are composed of glass tubes. which is having a diameter of 8 to 25 microns. Okay, and this is typically of honeycomb structure. Okay, so in the right side I am showing you a typical MCP plate, and you can see that these are having a hexagonal array of distribution of glass tubes, and these glass tubes are called typically called channels. So this is a 2-dimensional projection. Okay, but in 3 dimension it is actually a glass tube. You can see a single tube here, first tube, second tube, third tube. So it has a certain thickness. Okay, so this is the cross section image of a typical multi-channel plate. Okay, so and these are the glass tubes. Now these glass tubes at this surface, the surface of the multi-channel plate, both at the front and the back, these are covered by a thin conductive layer, which is a nichrome layer. This is a conductive layer. Okay, this is a conductive layer, and a voltage is applied across the surface, from this surface to the back surface. So this is a front surface, this is the back surface. So a voltage is applied between these two, bias voltage is applied between the MCP, so the surface of the MCP plate. Fine. What is the role of this bias voltage? I'll describe in a few minutes. Okay, and these multi-channel plates are aligned at a certain angle, which is around 15 to 5 degrees. I will come to this in the end of the lecture, that why these are aligned from 15 to 5 degrees to the normal axis. Okay, so in the left side you can see that this particular schematic, the cross section schematic of a typical multi-channel plate, and you can see that if this is a normal, then if this is a normal, then these multi-channel plates are aligned between the 5 degrees to 15 degrees. Okay, so now as I talked about that, so this black color shade area, this is a nichrome layer. Now if you apply a voltage between the two surfaces of the multi-channel plate, the front part and the back part, and the voltage applied is typically of minus 0.8 to 1.2 kilovolt. Across this application of voltage across the front and back part of the multi-channel plate, it will create a very high surface charge density, very high surface charge density on the surface of the glass tube. Okay, so this is your channel, and a very high surface charge density will be created on the surface of the charge tube. Okay, so at the middle I am showing you one multi-channel, one glass tube, which is a part of a multi-channel plate, where you can see that there on application of a very low bias voltage between the front part and the back part. Between the front, this is the front, this is the back part, negative voltage of around 0.8 to 1.2 kilovolt, you will induce a very high amount of surface charge density on the glass tube. This is the glass tube, on the surface density on the glass tube. Okay, so now what will happen is, if a ion travels along this direction, okay, if a ion, positive ion, gas ion travels from the tip surface towards the multi-channel plate, what will happen? These ions will strike on the will strike on the surface of the glass tube, and as you know, this glass tube is heavily surface charged density, is having a very high surface density. Due to the striking of ions on the surface of the glass tube, which is having a very high surface charge density, they will emit a very high number density of secondary electrons. As you can see in the schematic at the middle, if there is an incident ions which is striking on the surface of the glass tube, there will be a very high number of secondary electrons which are generated from the glass tube. And out of these secondary electrons which are generated, a single electron can strike back to the surface. So can strike back to the surface to produce 1,000 more number of electrons from the charged surface. So this is how a cascade of electrons will travel along the glass tube. And due to this electric field which is applied between the surface of the MCP plates, this cascade of electrons will travel across the channel towards the phosphor screen. So this is the function of a typical glass tube, which is one of the glass tube which is present in the very large number of glass tubes in an MCP plate. So when these electrons are coming out of the MCP plate, so assume this is an MCP plate, okay. So when the electrons, these are MCP plates, when the electrons are coming out of the MCP plate, okay, these has to be converged to a spot. For that purpose there is a phosphor screen, okay, and this phosphor screen is coated with a transparent conductive layer, which is might be of indium oxide or which is mostly a indium oxide. Fine. So these electrons, then what will happen, if you apply a bias voltage across the back end of the MCP plate and the phosphor screen of few kilovolts, then what will happen is these electrons which is having a spread, they will convert to a sharp spot on the phosphor screen by application of a bias voltage, again bias voltage between the back end of the MCP plate and the phosphor screen. So this is due to the this is main function is to reduce the lateral spread of these electrons which are coming out of the MCP plate from the back side, okay. Then these converged electrons which are on the spot, these spots actually hit to the fluorescent screen. As I told you, the energy, the typical energy of an emitted or the photon emitted by electron is 0.5 photons per electron, which is much higher than 0.01 photons per ion, okay. So and it produces a very bright spot on the phosphor screen, and it does not damage the phosphor screen. That is why we use MCP plates, MCP, which avoids the direct contact of ions on the phosphor screen, okay. So as a common sense we can see that the deficiency, the detection efficiency of an MCP can be directly correlated to the area of the open space or open channel across the MCP plate. Fine. The fraction usually it is around 50 to 60% open channels on the MCP plate, okay. And one more thing to remember is the one ion, the multiple ions or the multiple ions can contribute for a one particular spot on the phosphor screen. Correct. So the MCP, the detection efficiency of the MCP plate is directly related to the open channel space on the MCP, and which is around 50 to 60%. So remember, again I told that these channels are actually oriented around 15 to 5 degrees with respect to the normal axis. Imagine that imagine that the channel plates are aligned exactly along the normal axis. So what will happen? The tendency of the ions to striking the glass surface or the glass tube will be very minimum. The ions can travel along this normal axis easily and hit to the phosphor screen. But if you keep these channel at an angle, then the efficiency of hitting of ions on the glass surface will significantly increase, and which results in a very high density of electrons coming out of the multi-channel plate. Fine. So with this I will end this class now. I hope that you understood the importance of the instrumentation in FIP, and what are the basic things which are required to construct a proper basic FIM microscope. Okay. In this, the most important is the important points are these are in the ultra high vacuum, cryogenic temperature, then use of a high DC voltage, sharp tip, imaging gas should be at a lower pressure, and the use of MCP multi-channel plates just ahead of the phosphor screen, so that you will have a large amount of photons released on the phosphor screen without damaging the screen. Okay. So we will meet in the next class, and I will proceed with how to interpret the FIM images for a solid solution or for an element or a multi component or the multi phase alloy. Then we will meet in the next class. Thank you.